In this video, we'll take a look at an introduction to mathematical proofs and justifying our reasonings with steps. We'll look at new postulates as well. We've already discussed in our previous lessons the ruler postulate, segment addition postulate, protractor postulate, and angle addition postulate. We have 7 new more postulates to take a look at. The first one is through any 2 points there exists exactly one and only one line. This abbreviation is for one and only one line. Number 6, a line contains at least 2 points. Number 7, if 2 lines intersect, then their intersection is exactly one and only one point. Through any 3 non-collinear points, there exists exactly one and only one plane. Number 9, a plane consists of at least 3 non-collinear points. If 2 points lie in a plane, then the line containing them lies in the plane. And number 11 is if 2 planes intersect, then their intersection is a line. Now, a lot of these sort of sound like they're saying the same thing, but it's about what comes first, what comes second. So as we take a look at our drawings, we have what postulate is illustrated. If it looks like 2 lines intersect, then, notice this is highlighted, then 2 lines intersect at a point. That was postulate number 7. If 2 lines intersect, then their intersection is at one and only one point. Can you guess the next one? If 2 planes intersect, then they intersect at a line. This is postulate number 11. If 2 planes intersect, then the intersection is a line. Here we have, if we have a line, then it's going through 2 points. Let's see what postulate that is. A line contains at least 2 points. That's postulate number 6. So can you guess this next one? We've got 3 points. Then those 3 points are on a plane. This is postulate number 8. Through any 3 non-collinear points, there exists one and only one plane. Again, we have 2 points, and we have a line drawn through them. So this is something like if there are 2 points, then we can draw exactly one line through them. That's postulate number 5. And then we have, if we have a plane, then it's made of at least 3 non-collinear points. Use the diagram to write examples of postulate 9 and 10. Postulate 9 says a plane contains at least 3 non-collinear points. So if we take a look at plane, P, for example, plane P is a plane because it consists of at least B, A, and C, these 3 non-collinear points. If we have postulate 10, if 2 points lie in a plane, then the line containing them also lies on the plane. So if we have 2 points, B and A, that are on the plane P, then the line BA is also on the plane. So here's some examples. Point A, B, C define plane P. A and B define line N, which lies in plane P. We're going to take a look at some diagrams and see what kind of assumptions that we can and cannot make. So here we have a plane. It looks like we have plane P. I see lots of different points on that plane. And I see lots of lines. I've got 3 lines. We have line, it looks like H and F. We have line C and E. We have line A and D. H is going to be this point of intersection. J is going to be that point of intersection. We also have point G kind of hanging out in space, but also it looks like it's on the plane. So what can we assume here? Let's take a look at what we can assume. We can assume that all the points are coplanar. They all look to be on plane P. It says angle AHB and BHD are a linear pair. So angle AHB and BHD make a linear pair. I agree with that. So we've got this angle with this angle that makes that linear pair. You could say other angles as well. AHF, FHD, they make a linear pair. BHA, AHF, they make a linear pair. There's lots of other linear pairs that you can also assume from this picture. We can assume that AHF and angle BHD are vertical angles. So AHF, that's this, and BHD, that's this one. Do they make a vertical angle? Yes, they do. And that means they're congruent. So that's one of our vertical angles. We can also label the rest if we wanted. This with this is a vertical angle. We can say this one and this one make a vertical angle. We could also say this and this make a vertical angle. We can say that A, H, J, and D are collinear. A, H, J, and D are definitely on that line. We can say that A, D, and B, F intersect at H. So A to D and B to F intersect at point H. We could also say that A to D and C, E intersect at point J. Now let's take a look at the things we can't assume. We cannot assume that G, F, and E are collinear. I mean, they look like they can make a straight line, but I can't assume that because I don't have a line drawn in the diagram. We can't assume that BF and CE intersect. BF and CE, we can't assume that at some point they're going to intersect and cross. We also can't assume that BF and CE will not intersect. We don't know that these lines are parallel. There's nothing to show parallel on here, so I don't know if they intersect. I don't know that they don't intersect. Angle BHA, this one, is congruent to angle CJA. We don't know that these two angles are congruent. I also have that AD, line AD, and line BF are perpendicular or form right angles there. So this is AD. This is the symbol for perpendicular, BF. So it's kind of like an upside down T is your symbol for perpendicular. So line AD and BF. We don't know that they form right angles. We don't know that any of the angles are 90 degrees, so I have that notation here as well. If they're not 90, then they're not perpendicular. We can't assume that either. So let's try and see if we can say true or false to the following statements using this diagram. CEF and FED. CEF and FED are linear pairs. Is that true or false? That one you can assume to be true. Angle CEF is congruent to angle FED. Do we know they're congruent? That one would be false. We don't have any degrees marked, so we don't know what their measurements are. We do know that they make a linear pair, but that's all we know. CD is equal to BD. So the length, it looks like, from C to D is the same from B to D. Do we know those lengths are the same? We don't. We also don't know that they're not the same. There's nothing on the marking to show congruence or equals. Line FG and CD intersect at E. So here's FG, here's CD. Do they intersect at point E? They sure do. That one's true. CEF and GED are vertical angles. CEF and GED. Are they vertical angles? By definition, they are. And our last one here, line FG and BD do not intersect. Line FG and BD. Is that true or false? That one would also be false. We don't have enough to say these lines are parallel or that they're not, so we just don't know. We just don't have enough. We also want to be able to sketch drawings from given information. So let's see. It says sketch a diagram showing that line TV. So I'm going to draw a line. And I'm going to label it T and V. Intersect segment PQ at point W so that TW is congruent to WV. So T to W has to be congruent from W to V. Well, I need to show those segments are congruent, so I'm going to add those lines. And I also need to add segment PQ. It intersects at W. So I'm going to draw my segment P and Q. Now I could draw that PQ and in any way that I want. It could be right up and down, it could be more on an angle. We don't know anything about the P and the Q, but we do have the rest marked. Here's another one. Sketch a diagram showing line AB intersecting line CD at point E so that AB is perpendicular. Sorry, that got a little perpendicular to CD. So we're going to draw AB. We're going to draw point E somewhere on AB. And then we're going to draw a line CD through E and say that it is perpendicular to line AB. Now, I don't know if it's perpendicular with what I've drawn right now unless I add in that right angle marking. So we need to add that in to be sure. You can only assume a line is perpendicular to another line or a plane if it's stated or marked with that right angle symbol. So you can see right in here, we've got a right angle symbol. I'll make that green so it stands out a little more. Which of the following statements are definitely true based on the figure? Now this is like a two-dimension drawn on a one-dimensional sheet, so it's hard to see all of this. But let's see, A, B, and F are collinear. A, B, and F, I can definitely see a line being drawn through them. F is on the blue plane. It's going up and down. So are they collinear? They are. E, B, and D. Can we assume E, B, and D are collinear? Is there a line drawn through it? No, we can't. That's false. Is line segment AB, this, perpendicular to plane S? Well, I do have that perpendicular marker. That one is true. Is CD perpendicular to plane T. CD perpendicular to plane T. Do I have a perpendicular marker there? I do not, so that one's false. Does AF intersect BC at point B? That is true. AF definitely intersects BC right at that point B. Pause the video and go ahead and try all of these examples and then unpause to check your answers. Example A, through any 2 points there is one and only one line. If a plane contains at least non-collinear points, is our second one. Draw a diagram showing that WX intersects VW at point T such that X, Y, VW are perpendicular. So we have to have that perpendicular marker there. Does WT have to be congruent to TV? And the answer to that is no. We don't know if it's a bisector. I didn't give you any of that information, so we don't know really where the length is on that. Use your diagram to determine if the statement is true or false. Planes W and X intersect at line KL. They do. Points Q, J, and M are collinear. Q, J, and M. Nope. M is not on the same plane as point Q. Points K, L, and M and R are coplanar. R is not on the same plane as the rest, so that's false. Line MN and RP intersect. We don't know that they do, so we have to say false there. RP is perpendicular to plane W. I don't see any perpendicular markings there to indicate that, so that's false. JK lies in plane X. That is true. Here it is, J to K. It's definitely on this lighter gray plane. P angle, PLK is a right angle. PLK, is that a right angle right there? We don't know, that's false, there's no marking. Angle NKL and JKM are vertical angles, and that is true. We have this angle and this angle. Angle NKJ and JKM are supplementary. Angle NKJ and JKM are supplementary. They sure make a linear pair. And then we have angle JKM and KLP are congruent angles. We just don't have enough to prove that they're congruent. The next thing we're going to do is take a look at justifying our reasoning, and we're starting the proof process. We're going to use a 2-column proof where we have statements on one side numbered and reasons to the right of that also numbered. The first statement will always be given for the reason. What's the problem? Oh, it's right there. That's given to me. As we work on this, what's happening? For my first line of work, it looks like I distributed. So that would be the distributive property. After that, what did we do? Well, it looks like we combined the x's. So that might be a step called simplify. We're just simplifying the math there. After that, we're subtracting 21 on both sides. If you're subtracting on both sides of an equation, you're using the subtraction property of equality, and I abbreviate that throughout my notes. Lastly, we're dividing by 11, so that's the division property of equality. And this would be your first proof. Let's justify segment addition. Next, we have AB equals CD, that's marked on my diagram. And we need to show that the segment AC is equal to the segment BD. Our first statement is given to us, and our second and third statement are the segment addition postulate. AC is equal to AB plus BC. BD is equal to BC plus CD. Now, my next line of the proof actually refers back to the first line of my proof. I'm taking AB and adding BC to both sides of that equation. So if I just take these out for a moment, I'm adding BC to both sides. That's what we have here. That's using the addition property of equality. We're adding BC to both sides. Now, how am I getting down to AC and BD? This is the substitution property. Here's why. AB plus BC, that's this. We can substitute this right here, AB plus BC. That's equal to AC. So that's coming right there. This second side, CD plus BC, well, if I look at my notes, CD and BC here are equal to BD. So again, I'm just substituting my values, and I'll get the proof for these line segments. Justify the reasoning. We have the measure of angle 1 is equal to the measure of angle 3. Determine whether the measure of EBA is equal to the measure of DBC. Our first statement in a proof is always given. Now let's take a look at the next one. It says the measure of EBA, so EB to A, is equal to the measure of angle 3 plus the measure of angle 2. That's your segment, or sorry, not segment, but angle addition postulate. Next, we're going to take a look at EBA. EBA. It says it's equal to the measure of angle 1 plus angle 2. Now, why would that be the case? I thought it was 3 with 2. Well, if we look back at our diagram, we can see that angle 1 and angle 3 are marked congruent. So we're taking angle 3 and replacing it with angle 1. This refers back to my original statement. This is your substitution property of equality. We're just replacing this 3 with the 1. Next, we have the measure of angle 1 and angle 2 is equal to the measure of DBC. DBC, angle 1 plus angle 2. That's your angle addition postulate again. And let's see, now that we have all of that information, how are we getting to that last line? The measure of EBA is equal to the measure of DBC. Take a look at line 3 and 4. EBA is angle 1 and angle 2. DBC is also angle 1 and angle 2. So that's called your transitive property of equality. Sometimes students also will use substitution property of equality, and you'll be given one or the other as an option. So you can use both of them sort of interchangeably, and that'll be fine for us this year. So you could also say substitution. You try the next proof. This is on segments. WY equals XZ. So this segment is equal to this segment. So I'm going to kind of mark it that way. Show that WX is equal to YZ. So let's see, we have YZ equals ZX. Then we have, YW equals XZ. That's given. YW is equal to YX plus XZ. This is segment addition postulate. And then we have that xz is equal to xy and yz. That's also your segment addition postulate. Now we have wx plus xy equals xy plus yz. So we are substituting or using that transitive property of equality. We had wx equals yz, or xz. Wow, let me start that again. wy equals xz. wy is wx plus xy. xz is xy plus yz. So we're just substituting this in for the wy. We're substituting this in for the xz, and we have this. So I'm going to say substitution property. Again, you might also say, this is of equality. You might also say transitive property of equality. And lastly, to get to the wx and the yz, this part and this part, notice that we have the same x and y on both sides of the equation. So our last step is actually to subtract those, get them out of there. So we're left with wx equals yz, and that's your subtraction property of equality. Given angle 1 and angle 4 are equal, the measure of EHF is 90 and GHF is 90, show that angle 2 is equal to angle 3 in measurements. So take a moment to see if you can come through, think through this proof. You'll notice there's one statement that's missing that you need to come up with, but I've given you the property or the reason that works with that. So pause the video, take a moment, and see if you can figure out what goes here. Angle 1 and angle 4, EHF 90, GHF 90, those were given to us. Then we have the measure of EHF is equal to the measure of GHF. That's your substitution property. Since they're both 90 degrees, we can say they're equal to each other. Then we have the measure of EHF is equal to angle 1 plus angle 2, which is your angle addition postulate. GHF is equal to the measure of angle 3 and angle 4, again, angle addition postulate. So now let's take a look. We have this is equal to that. We have this is equal to that. Therefore, these pieces have to be equal to each other. That's your substitution property or the transitive property. Now we have angle 1 and plus angle 2 equals angle 3 plus angle 4, but we've changed angle 4 to be angle 1, and that comes from our given statements. Angle 1 and angle 4 are equal to each other. So again, I'm using the substitution property to switch angle 4 with angle 1. Now, if you notice, we have the measure of angle 1 on both sides of our equation. So we're subtracting the measure of angle 1 from both sides of our equation. So that's using our subtraction property. And we're left with angle 2 equals angle 3 in measure.